Hey, pre-calc students, this is going to be unit for a day 4, and we're building off of what we talked about yesterday, which was solving quadratic inequalities and solving quadratic equations in general. Yesterday, we mainly looked at inequalities from an algebraic perspective. Today, we're just going to do a little bit more with our calculator to kind of see if the solutions that we get are maybe not such nice values, how we can justify and still come up with answers. So for this first example here, we're going to approach it from two perspectives. We will do it algebraically first, since that's the way we know how to do it. And then I'll also show you how we're going to do this one graphically. But we are taking notes by hand. So if you want to get some paper and get yourself started here, the very first thing we want to do is, if you remember algebraically, we have to set the inequality to 0. So I'm going to add the 6 over to this side. And then we have to find out the zeros, right? So we have to partition around the roots. And in order to do that, we have to try and factor this expression. So in this scenario, I don't really love factoring with a negative in front of the x squared. So we did this in one example yesterday, where if you just divide both sides by -1, you can now change this to x squared plus x minus 6. But you just have to be really cautious that if this is a technique you're using, you remember that dividing by negative means switch the sign of the inequality. So now we're solving when is this less than 0. And in order to figure that out, we're going to go ahead and factor this. So this would be x plus 3 times x minus 2. And it turns out that the two values that make this equal to 0 are at x equals -3. And at x equals 2. So we put those on a number line so that we can start our partitioning process. Remember that those should both have open circles, because if equal to 0 is not included, right, if these 0 is not included, we don't want to include either of those solutions. And then from there, we're going to test. And we did a lot of testing yesterday, so pick something to the left of -3, like -4. -4 plus 3 is negative, and -4 minus 2 is negative. Negative times negative is positive. We're going to get really used to this process, especially since we extend this in future units as well. If I test 0, 0 plus 3 is positive, 0 minus 2 is negative, and it's probably no surprise that in the last section we get positive, positive for something that's altogether positive. I don't want you to assume every time it's plus minus plus. In a lot of situations it will be, but there are going to be some rule breakers eventually. What did we actually want in this scenario? We wanted something that was less than 0. And less than 0 to me means negative. So less than 0, the negative region is everything between -3 and 2. So the solution here is, with parentheses, -3 to 2. So what I said today is, we'll certainly be able to do some of these algebraically, but what if I wanted to approach this and I said solve graphically? The nice thing about being able to solve this graphically, I'm just going to recopy this over here, is that you don't need to do any rearranging at all. You could actually go right to the calculator and look at this as a y1, y2 case. And what I'm looking for is, if I want to look at the quadratic on this side, where is it above? Where is it greater than this constant value of -6? So I'll make a kind of a quick sketch of what that looks like in just a second here. But I'll tell you, I at least know the line y equals -6 is going to look something like this, right? So there's y equals -6 for my y2. But to figure out what's going on in y1, let's go ahead and go to y equals. We can enter -x squared minus x into y1. And let's type in -6 to y2. I'm going to hit zoom 6. I have no idea what window I used last. So we get our upside down parabola. We're not super surprised by that, right? Because of the -x squared. And we can see that the line y equals -6 came across the way here. So if I go ahead and sketch that, let's see, we had a point of intersection here, a point of intersection here. And it looks like the vertex kind of like happens pretty close to the origin. So the graph looks something like this. Okay, and there's the graph y1. So graphically, I can tell we have 2 points of intersection. If I go to second trace, I can calculate those intersection points. Okay, second trace brings me to calculate. We want option 5. Scroll near one of the points of intersection and hit enter 3 times. And it's no surprise we get x equals -3. If you repeat that process on the other side, you should find that x equals 2 is the other solution. So we know that this corresponds with x equaling -3. This solution corresponds with x equals 2. And I hope that it's pretty clear that if I want to know where is the parabola bigger above -6, it's everything in between -3 and 2. That's when the parabola is above the line. If I had said less than, it would be everything outside of -3 and 2. That's when the parabola dips below the line. So certainly we can confirm our results algebraically, like we learned yesterday, but today we'll take a look at a few more examples graphically too. So speaking of graphically, let's actually do the entire next example from a graphical perspective. All right, so in number 2, I'm going to ask you to actually do a few things. So we'll break this down to kind of parts like A, B, and C. In part A, we're going to find out where does x squared plus 4x minus 2 equal 2x plus 1. And in part B, we're going to solve where is this quadratic less than 2x plus 1. And then in part C, we'll do the same thing, but where is it greater than or equal to 2x plus 1. Okay. If I said let's do it algebraically, the approach would be set it to 0, right? Move everything over, factor, get your solutions. And then whatever those solutions are, that's the answer to part A. X equals this and x equals that. In parts B and C, you would then put those numbers on the number line and do your partitioning and see where is it less than and where is it greater than. In other words, where is it negative, where is it positive? But if we're approaching things from a graphical perspective, we're going to put y1 on one side, and we'll do the other side as y2 and see what happens. We know this is a parabola, and we know that this is just a straight line. It's of the form y equals mx plus b. So I'm going to go ahead and quickly draw a set of axes here. And let's go right to y equals and change what we have in there from the first example. So we've got y1 x squared plus 4x minus 2. In y2, we need 2x plus 1. And again, you don't necessarily have to zoom 6 again. Just hitting graph should bring you to the standard window. And there's my parabola. And this is the line y equals 2x plus 1. So we can pretty, I think, clearly and nicely see here that we have 2 points of intersection. So I'm just going to see if I can do my best to reproduce this graph over here. So we have an x-intercept that's negative, and then over here. So we get a graph that looks like this for y1. And it doesn't have to be a super accurate sketch, but try and at least find the points of intersection in the appropriate location. So the points of intersection in my diagram look like they're approximately in those spots. So we've got y1 and y2. All right, so that looks pretty good. So from there, to answer part A, where are these two functions equal? Let's calculate those intersections. So the intersection on the left side, if I hit enter 3 times, 1, 2, 3, is that x equals -3. So we'll keep that in mind. Go back to second trace and do intersect again for the intersection point on the right side. And that intersection, 1, 2, 3, occurs at x equals 1. So the way that I'd like you to write your answer to part A is you're going to write it as a solution set. So since the only values that make this true are x equals -3 and x equals +1, use a set of curly brackets to represent that those are the only two values there. So we know that this is x equals -3. We know that this happens at x equals 1. All right, in the next step, I want to figure out where is the quadratic less than 2x plus 1? In other words, where is the parabola underneath the linear function? And you can see it's underneath, it dips below the line, in between -3 and 1. So the way that you'll write your answer to this inequality is everything between -3 and 1. Notation, notation, notation. It's important to separate curly brackets versus parentheses. They mean something different. This represents all the values between -3 and 1, but not including those values. Whereas this notation is just -3 and 1. Okay, and then finally, then the last piece is, well, where is the parabola above the line? Everything outside of x equals -3 and x equals 1. So from -infinity up until -3. you can include it because it's an equal to, right? And then everything from 1 to infinity, the parabola will be above the line. So hopefully graphically that makes sense. We've done this with 2 lines so far, maybe not with a line and a parabola yet, but the graph can help you to justify those results there. Okay. All right, let's do just a little bit more with graphical. Actually, you know what? I'm going to encourage you to do one. Let's see. I'm going to have you try solving pi x squared, pi, minus 3x minus radical 80. I want you to tell me, where is this less than or equal to 0? And I'm going to ask you to do that to the nearest hundredth. You're not going to get really nice answers to this, but I do want to see if you can do this part on your own. You want to compare this to 0, the x-axis essentially, and see when this is less than or equal to 0. We'll go over this in class next time I see you. But actually, I want to try one more algebraically because I think there's a question that comes up like this on your homework. So it would be good to address something like x squared plus 6x plus 4. Where is that greater than or equal to 0? All right, what we've done with every other case algebraically so far is we factor, right? We set it to 0. Well, I mean, this one's already set to 0, so that's good. But we set it to 0, factor it, get those 2 solutions and put them on a number line. And what you'll find really quickly in this example here is that it's not factorable. But have no fear. We can still get the solutions by either quadratic formula or CTS. I'm going to set this equal to 0 to find the 2 roots, find the 2 x-intercepts, and I'm going to do it by using CTS. So I know it says greater than 0, and we're going to come back to that, but we first have to find those 2 points that we're partitioning around. So I'm going to subtract 4 to the other side. And I like CTS because the coefficient of x squared is 1 and b is even. Those are my 2 reasons for choosing CTS. Take the middle term, divide it by 2, and then square it. That's 9. So you're going to add 9 to both sides. Okay, you don't have to write that off to the side unless it helps you. This becomes x plus 3 squared equals negative 4 plus 9, which is 5. Square root of both sides gives you x plus 3 equals plus or minus the square root of 5. And then finally, that last step, subtract the 3 over. The 2 solutions of when this equals 0 are at negative 3 plus or minus the square root of 5. Okay. How do I then take those solutions and get the solution to when this is greater than or equal to 0? Well, we've got to put those on a number line. Negative 3 minus the square root of 5, and then negative 3 plus the square root of 5. Those are your 2 solutions that we're going to partition around. Now, to figure out the partitioning successfully here, we need to think about, what's the approximate decimal value of these? And I think you guys can probably reason your way through this, that if the square root of 4 is 2, the square root of 5 is a little bit bigger than 2. So negative 3 minus 2 point something is going to be negative 5 point something. And if you're really hesitant about that, just type it into the calculator for now. Negative 3 minus the square root of 5 is negative 5.23, okay? But knowing that it's negative 5 point something, all that tells me is over here, I'm going to choose go crazy. Choose negative 10 if you want. So if I choose negative 10, here's the only thing. Usually we plug that negative into the factored form. And we say, oh, it's negative times negative or positive times positive or whatever it might be. We don't have a factored form. So where do I plug in negative 10? Let's go all the way back to the original and see if it's positive or if it's negative. And negative 10 squared is 100. Then you would get minus 60 plus 4. Well, 100 minus 60 plus 4, even if you don't know what that number is, we know that it's positive. Now, by the way, negative 3 plus the square root of 5, that's still going to be a negative number, isn't it? Because radical 5, we just decided, is a little bit bigger than 2. So it's going to be some decimal value. So negative 3 plus the square root of 5 is negative 0.76-ish approximately. So when I choose a number in between, maybe I'll try like negative 3. That might work. Negative 3 squared, that's going to be 9. But then you get minus 18 in the middle. That's negative 9 total. And negative 9 plus 4 is still a negative number. You choose 0 out here. 0 is pretty easy because you're just left with 4, which is positive. And now that I see the partitioning here, even though it wasn't as easy as if it were factorable, I can see that this is greater than 0, meaning positive, in these regions out here. This region and this region. Now, when I go to write my final answers, I don't want you to use the decimals. The decimals were just helping us to pick our partition points. What I do want you to use are the exact values here. So the final answer to this would be that we're greater than or equal to 0 from negative infinity to the first solution, negative 3 minus radical 5, include it with a bracket, and then from negative 3 plus radical 5 to infinity. And I realize that's kind of ugly looking to us, but at the end of the day, you can still solve a quadratic inequality even if the solutions are irrational, like we had in this case. Okay, so I wanted to model that for you because, again, I'm pretty sure there's something like this on the homework, so don't be afraid of it. If you need to refer back to what we did in the notes, certainly come back to this example right here. We're going to do one more thing in this lesson, and it's a familiar concept to us, but we haven't done it with quadratics yet. So that familiar concept I'm talking about is rewriting an absolute value function as a piecewise function. We've done this in the functions unit, but we've only done it if it's linear on the inside of your absolute value. Now we're going to toss in a quadratic function on the inside, and we're going to see how that changes things a little bit. So here are the steps that we're going to take if we have the absolute value of a quadratic. To rewrite it as a piecewise, the first step is find the zeros. I mean, that's what we've been doing all along. We're going to find the roots, find those x-intercepts, and then you're going to put them on a number line, just like we've been doing in the other situations where we've been solving inequalities. So where you get a positive on the number line, your equation stays the same. Because remember, if you get a positive output, the absolute value of a positive is still positive, so the equation would not change. But if you test the number and you get a negative on the number line somewhere, what you have to do is negate that equation, because negating something that's negative would turn it into something that's positive. And I think that's maybe a little bit abstract to us. I hope it will make sense once we look at the graphical representation here. So the directions might say something like rewrite. This would say, this is without, by the way, rewrite without using the absolute value. And don't get all cutesy on me and just drop the absolute value bars and say I'm done. When we say rewrite without using absolute value, it really means rewrite it as a piecewise function. Break it up into two pieces. So let's follow those steps and see if we can do this. First thing says find the zeros. Well, it's pretty easy to do if it's in factored form, isn't it? Because the zeros in this case would just be 3 and -1. So we're going to toss those zeros on a number line. And then you're going to do that partition step. By the way, you don't need to open or close circles. That doesn't really matter here. But let's just test where we're positive and where we're negative. If I test -4, -4 minus 3 is negative. -4 plus 1 is negative. And you're going to see some very similar patterns come up here. So this first region's positive. Then in between -3 and 1, if we test 0, we get negative times positive, which altogether is negative. Last region, test 2, you'll get positive, positive, which is altogether positive. And now to rewrite this without using absolute value, to write it as a piecewise function, we're going to follow the rules that I wrote up here. Where we got positives, which is outside of -3 and 1, the equation is the same. Where it's negative, we need to negate the equation. So here's what this is going to look like. Let's start with the positive first. We're going to write f of x equals. Give me a curly bracket there. We're leaving the equation the same, so it's x minus 3 times x plus 1. When what happens? When x is less than or equal to -3, and when x is greater than or equal to 1. So when we're to the left of -3, and when we're to the right of 1, we're going to see this graphed. What's happening in between -3 and 1? Well, in between -3 and 1, we're going to have to negate the function. How do I negate this function? It's real easy. Put a negative out front. There you go. So we're going to see the negated form of this when x is between -3 and 1. So that would be -3 is less than x, which is less than 1. How do I know if I should put the equal to up here or the equal to down here? It doesn't matter. Just like for linear, as long as you put it with one or the other, it doesn't matter where you put that equal to piece. I really quickly want you to think about what the graph of this looks like here, because we've done absolute value before, haven't we? We know that this graph has a root at -1, or sorry, negative. Did I do this wrong, guys? Darn. Nobody was here to stop me. Shouldn't this be reversed? Wasn't this supposed to be -1 and +3? I got so excited. And now I'm really sad about this, because this is all wrong. All right. We'll fix it tomorrow. Oops. All right. Well, listen, if this is my first major mistake in a video, it won't be the last, but we'll fix this one tomorrow. Sorry about that. Luckily, we have another one that hopefully I can save us on, but this should have been -1 and +3. This whole thing, I mean, it's not that bad of a fix, but let's just put it to you this way. I'm going to need some white out to fix it. Okay. Never mind. Let's go ahead and take a look at one more. Hopefully, I'm not going to mess this one up. Number 2. The function g of x is equal to the absolute value of x squared minus 5x plus 6. So there's really just one initial starting step that we have to do here that we didn't have to do in number 1, because number 1 was already given in a factored form. So let's go ahead and factor this. So this would be, if I factor it, we have to multiply to +6 but add to -5. That's going to be x minus 2 and x minus 3. Be a little bit careful about that, right? But those multiply to +6 and they add up to -5. All right, I'm going to slowly put these numbers on the number line here because I made a mistake with that a second ago. The solutions would be at 2 and 3. Pretty confident about that. If I test something to the left of 2, like 0, we get negative times negative, which is positive. In between 2 and 3, we got to choose 2.5, I guess. 2.5 minus 2 is positive, but minus 3 would be negative. So there's negative there. If I choose 4, you get positive, positive. So looking at the number line, how do I then translate this into a piecewise function? And then hopefully I'll be able to show you the graph. Okay, where it's positive, the equation stays the same. And you can go to the factored form if you want, or back to the original, it doesn't matter. If I go back to the original, it would be x squared minus 5x plus 6. We're going to see that when x is to the left of 2, so less than or equal to 2, and also when x is to the right of 3, greater than or equal to 3. We're going to see the negated form of that where we got the negative. So you can just put a negative in front of this whole thing, or you can just negate every single term. You'll probably see me write it more often like this in my answer keys. So just negate everything. Negative x squared plus 5x minus 6. You're going to see that graphed in between 2 and 3. So when 2 is less than x, which is less than 3, right? These are all my values of x in between 2 and 3. All right, this I'm pretty sure is correct. I feel confident about that. But just to think about what the graph looks like, if we think about having roots at 2 and 3, the parabola will look something like this. What does absolute value do to a parabola? Well, remember, for absolute value, we turn up. This part would stay the same, but all this part underneath the x-axis would turn up and look like that. This part would stay the same. Right? The parts that are positive stay in place. The parts that are negative flip up over the x-axis. So notice how when I'm to the left of 2 and to the right of 3, we're keeping that parabola identical. But in between 2 and 3, we had to flip that parabola over when we take absolute value to make all those y values positive. The way we do that is we negate the whole expression. So hopefully that makes sense to you. So sorry about number 1. I promise we'll fix it tomorrow. No big deal. But you could probably fix it really quick just by adjusting these values. Should be a -1 and a +3. All right. Let me know if you have any questions about this lesson. We'll make some quick fixes tomorrow.